Hi, and welcome to Trial by Air. I'm Ryan, and my co-host Rhythm and I are aerospace engineers. We want to share our knowledge and experiences in the field of aerospace engineering, but more importantly, we want to bring to you the knowledge and experience of experts in their field. We started Trial by Air to learn more about applied and theoretical engineering, and hopefully, when you come along with us, we can do a good enough job of explaining it so you can learn something too.
In 1853, Sir George Cayley, known by some as the father of aviation, designed a glider that carried an adult across Bromptondale, England. With this, he set forth the notion of fixed-wing flight, with separate systems needed for lift, propulsion, and controls. As such, he is accredited for discovering and determining the four fundamental forces that govern the motion of flight: thrust, weight, lift, and drag. In today's episode, we're going to be talking about these four fundamental forces. All analysis really begins with these four fundamental forces. Aerospace engineering is sort of like a science that attempts to optimize and balance these four forces. We want to minimize the weight and drag and increase thrust and lift. From the first demonstration of these fundamental forces, we've come up with a lot of different ways to achieve the optimization. Each aircraft that we see fly, and will see in the future, are really manifestations of these optimizations.
Before we start today's episode, let's jump into some aerospace news.
So there's some good news for Boeing this past week. The Boeing 737 MAX aircraft had been grounded by the FAA and the European Union Aviation Safety Agency after a 20-month-long grounding. That's really cool to see. Got to see that, 737 MAX is sort of kind of coming back into the aviation industry, because I know it's taken a big hit, or it's given a big hit to a lot of, aircraft or passenger, or rather commercial companies. What do you think about it?
I think it's pretty good, to be quite honest. I mean, they did have some issues with the safety culture and some of the designs they use, but now it's probably one of the most heavily scrutinized planes in history, and that's not even a stretch to make that assumption because of all the analysis the FAA did and Boeing did to cooperate with them, and them just trying to help these carriers and commercial airline providers, because there are a lot of budget airlines that rely on a single variant operation, Southwest in the United States being known as one of them, where they only use one type of aircraft, which is the 737, for their transportation predominantly. So when the MAX got hit, that hurt a lot of those companies. And it's just good to see that it's moving forward, and I hope it's moving forward for the right reasons instead of the wrong reasons.
Yeah.
And hopefully, not only is the plane safe, but the pilots who fly it are, they're even more conscious of the safety and the things they need to do to fly the plane safe. So I'm looking forward to it flying, and I really do hope it's going to be one of the safest planes in the air.
Yeah, no, I think you bring up a good point with the whole, increased scrutiny and all. I think, with the incidents that have happened in the past, there definitely have been changes made to sort of how aircrafts are, how they're certified to be able to fly. And I'm sure, those things will continue on to other aircrafts. That's not going to be just for the 737 MAX. I'm sure, they've, increased sort of the scope of how they analyze aircraft so that, things like, the MCAS system doesn't get cut or doesn't get missed, and they're able to make sure that some incidents like that can never happen again. And I also wanted to mention that I think it's a good step. I think I'd heard about this from somewhere, but a lot of aviation safety agencies have now sort of stepped away from the FAA and started making their own calls, right? I know that China's been doing that. I think Canada as well. A lot of other companies, I guess the European Union Aviation Safety Agency also did that. I'm not entirely sure if they followed through with the FAA just because the FAA certified it.
I think they ungrounded it just like the FAA, but they haven't certified it yet to fly, which is the FAA. I think the FAA has certified it to fly, but it could be wrong on that. Basically, the European Union is very tentative, and there's a lot of politics involved you don't have to get into, but it's definitely a political situation on top of a engineering and business.
Yeah. No, but like you said, I'm sure this will be a pretty safe aircraft to fly in the coming future, coming few months. Yeah. So I'm looking forward to seeing that beautiful aircraft fly again.
Yeah, and I'll just say this: I wish we didn't have to go through that level of scrutiny just to get an aircraft to be safe. So it should be safe from the
Exactly.
get-go. Anyway, but last week on November 14th, as many of you know, SpaceX launched its first operational mission of the Crew Dragon, Crew 1, to the ISS with a four-person crew made up of three NASA astronauts, Michael Hopkins, Victor Glover, and Shannon Walker, and a JAXA astronaut, Soichi Noguchi. And this was the first operational flight of Crew Dragon, and the name of the capsule was Resilience. I think it was named that after all of the pandemic-related issues and challenges that healthcare workers face, and it's kind of to honor them. And it's exciting to see the beginning of the commercial spaceflight program take off, quite literally and
Yeah,
figuratively.
yeah, yeah, well, for sure. I I'm actually really excited to see the commercialization of space. I've told a lot of my friends and peers that I think the moment that that actually happened was way back. Like I think this was when SpaceX did their demo launch with no astronauts, no crew in their spacecraft. I think it was just a pure Dragon capsule that was autonomously docked with the space station, which had like supplies and stuff. I forgot when this happened. I think this was a couple years back. But it was really cool to see that, and I justify that moment as the moment of the commercialization of space because this is when SpaceX was. I guess this was when a company for the first time. I don't think any other company has done this before, but like a company was able to dock with the International Space Station through NASA's, like it passed NASA's certification and whatnot, and docked with the International Space Station, and then came back safely. I thought that was a big moment, and I think commercialization of space is definitely going to allow for a lot more innovation, a lot less sort of meshing of politics into sort of the way we act and the way we do things in space. I also don't, but I don't know. I don't necessarily know if this will be like. I don't know if it's gonna be good or bad. I think it's gonna be good, but we'll see how it ends up. Kind of progressing as time goes on. You know.
Yes. Yeah, the responsibility now of providing the safety of the vehicle and the operation of the vehicle falls solely on SpaceX and now Boeing, who are working on their
Yeah.
CST-100 Starliner, which is the competitor to the SpaceX Crew Dragon, um, which you can argue the merits of and the detractions. But it is a big step forward because that means that NASA's budget can focus on better things other than sending people up to the ISS using Soyuz. It makes, when you destroy a monopoly, competition drives costs down and
Mm-hmm.
innovation goes up. So that's just a good thing in
Yeah.
general. And I think NASA should focus on stuff that is not as profitable, like going to the moon, going to Mars, which companies aren't aren't really profitable for. But I would like to say, just to make sure the notion isn't lost, that NASA funded this entire program and they paid for the first flights, and they do deserve a lot of the credit for what happened because this wasn't like Blue Origin where it happened in a vacuum and it was privately funded. This was a publicly funded project that allows other organizations other than NASA to catch a ride in the International Space Station at a lower cost. So, congratulations to SpaceX, and again, congratulations to NASA for not only funding this program but also working with them to make it a safe program. And with that, let's get back into today's episode. How does flying work? That is the question Sir George Cayley, as we mentioned in the introduction, sought to answer. But before we get into the four fundamental forces of flight, we need to introduce the concept of a free body diagram. A free body diagram is a method used to predict the dynamics of a system where forces are acting on it into a simple and easy to understandable concept that allows for quick and easy analysis. In our case, our free body diagram is a two-dimensional plane on which sits a 2D rectangle. The plane represents the medium that the aircraft is traveling through, and the rectangle is a simplified representation of our aircraft. Now, the forces acting on this rectangle are lift, which is pulling the rectangle up, and directly opposing lift, which is pulling the rectangle down, is gravity. The rectangle is traveling to the right in the plane, and pulling it to the right is the force of thrust, and opposing that force of thrust, pulling the aircraft to the left, is drag.
Of the four fundamental forces that Ryan mentioned, lift and drag are probably the most important and most studied forces in aerospace engineering. So let's talk a little bit about lift. The lift force is a force that opposes the gravitational force. During takeoff, the lift force is greater than the weight force to allow for the aircraft to accelerate upwards. During cruise, however, the lift force and the weight force are equal to each other. If at any moment the weight force is greater than the lift force, then we will see an acceleration downwards of the aircraft. Now, lift may sound like a very confusing and a complicated topic, but actually, you can define lift by a very simple and powerful equation. The lift force is equal to 1/2 rho v squared CLC, where rho is the density of the medium in which the object is traveling in, v is the velocity of the object, c is the characteristic length of the object, and CL is the coefficient of lift. Of all the parameters I mentioned, the coefficient of lift is probably the most important parameter that is studied widely throughout aerospace engineering. The coefficient of lift is a non-dimensional value that is used to describe how well an aircraft object can produce lift. It can be argued that the coefficient of lift is actually a function of the object geometry as well as the object's angle of attack. Now, when I say angle of attack, the way I like to describe angle of attack is, let's say you're taking off in an aircraft. The aircraft is pointed upwards at an angle, correct? But the aircraft is also moving forward while being pointed upwards at that angle. And so the angle of attack is basically the angle between that forward motion of the aircraft and the upward direction that the aircraft is pointing at. Now, I've mentioned a lot about this object. More often than not, the object changes depending on what kind of analysis we're doing. If we're doing a two-dimensional analysis, this object will be called an airfoil. If we're doing a three-dimensional analysis, this object will be just known as our wing. To keep things simple for this first episode, let's focus solely on two-dimensional analyses. So therefore, we'll be focusing on an airfoil. Airfoils are two-dimensional cross-sections of wings. Basically, they're arced in the front, and they come in conversion to a point at the trailing end. These airfoil sections are used to manipulate the flow such that it produces lift for us. The way an airfoil manipulates the flow around it can be best described by using Newton's third law of motion and the Bernoulli principle. As the airfoil travels through the medium, the airfoil deflects the flow downwards, and as by Newton's third law of motion, that airflow will have an equal and opposite reaction upwards, pushing the airfoil up. That's a very big picture understanding of how lift is being produced. But we can also look at lift locally at different points along the airfoil. And we can use Bernoulli's principle to understand what is going on locally. So to start, Bernoulli's principle states that the local static and dynamic pressure will be the same everywhere that you look. Now, when I say static pressure, I just mean the local pressure in the area. And when I say dynamic pressure, the dynamic pressure can be best described as 1/2 rho v squared, where v is the velocity of the fluid, and rho, like I mentioned before, is the density of that fluid. When we focus on the upper surface of the airfoil, we notice that the fluid is actually moving at a faster speed relative to the lower surface. And remember that by Bernoulli's principle, the static and dynamic pressure must be constant throughout. If there is an increase in the velocity, hence the dynamic pressure, there must be a decrease in the static pressure. And so therefore, because of the geometry, the airfoil upper surface will have a lower pressure than the airfoil lower surface. This pressure differential is a good way, or best describes what is going on around an airfoil as it moves through a medium. Now that we've talked about lift, let's talk a little bit about drag. Drag is a force that opposes the forward motion of an object. It can be thought of as being very similar to friction. We can describe drag using a very similar equation that we use for lift. Drag is equal to 1/2 rho v squared CD C, where rho again is density, v is the velocity of the object, c is the characteristic length of that object, and CD is the coefficient of drag. Coefficient of drag is a non-dimensional value that can be used to describe how much resistance there is as an object moves through a medium. Just like the coefficient of lift, CD is also a function of the geometry as well as the angle of attack. Drag is a complicated force, and a lot of different sources can create drag, but we like to classify drag into two major categories, form drag and friction drag. Form drag can be thought of as the drag that is created due to the shape of the object. The bigger and wider the object is, the more drag it will produce. For instance, an object such as a baseball will produce more form drag, whereas compared to a pencil, a thin, slender object. However, this is assuming that the thin, slender object such as the pencil, its overall length is parallel to that of the flow direction. If instead, the pencil is orientated where the tip of the pencil is pointing upwards and the body of the pencil is moving forwards, therefore the length of the pencil is perpendicular to the flow, then there would be a lot more form drag from the pencil. On the other hand, friction drag can be thought of as friction that is caused by the air molecules as they move over a surface. Imagine you moving your hand through a jar of marbles. As you move your hand through those marbles, you'll feel the marbles roll across your arm. However, that motion of the marbles rolling across your arm will also produce a sort of friction that is impeding your motion. So you actually cannot move as fast as you usually can when you move your hand through the jar of marbles. Similarly, as an object such as an airfoil moves through a fluid, the fluid molecules will roll along the object's surface. And this principle can be kind of extrapolated and grown into this idea of viscosity, but we won't go into too much detail about this, as we'll talk about this in another episode. Skin friction drag is also dependent on the roughness of the surface. For instance, a rougher object such as like sandpaper will have a lot more skin friction, whereas compared to a smooth, slender pencil, which will have a lot less resistance due to friction. That's why a lot of times when you look at aircrafts, they're extremely smooth because any sort of imperfection that appears on the surface can have a really, really big impact on how much drag the object produces. And more often than not, aircrafts are optimized to operate at a specific drag incident level. And so any indentations, any imperfections that occur on the surface can have a big impact. It is important to be mindful of how drag impacts an aircraft. Any wasteful energy that is used to overcome drag that was not accounted for in an analysis can be very, very detrimental to how efficient an aircraft is and how it functions and operates. And so therefore, aerospace has a very strong focus and importance that it places on drag itself. In future episodes, we'll make sure to talk a lot more about drag, as this is just a surface level introduction of what drag really is. Drag can be a lot more complicated, and there's a lot more details that have to be considered and understood when we think about drag, not only in a 2D sense, but also in a 3-dimensional analysis.
And finally, to discuss thrust. What is thrust? Thrust is the force used to push the aircraft forward or to pull the aircraft forward, depending on how you look at it. But how is thrust generated? There are a multitude of ways to generate thrust, and some of them we are very familiar with, like propellers, turbojets, and turbofans. So let's get into the principle on how thrust is generated. For propellers, thrust is generated by spinning an airfoil perpendicular to the direction of travel. And that means that the lift generated by that airfoil is pointing forward in the same direction that the aircraft is traveling. And propellers can be mounted on a multitude of things like internal combustion engines and turboprops, but we'll save those for a future episode. Now, the ones that we are very familiar with used on passenger airliners are turbojets and turbofans. Think of a turbojet as a series of fans used to compress the air going into the turbojet. And that is compressed into a combustion chamber where fuel is added and is combusted, and as it's leaving, it is expanded. And as it leaves, it expands through a turbine, which is spinning the compressor. And that expansion causes thrust. Think of it like this. If you have a balloon and you blow it up and you pinch the end of it, there's a pressure exerting on the skin of the balloon. And when you let it go, the balloon flies and does loops and stuff like that, right? But if you take that balloon and you're simultaneously blowing into it and letting it go, or unpinching the throat of the balloon, that is how a turbojet works. It is compressing and expanding the air. And that exertion of pressure when it compresses and the release of the expansion is what pushes the aircraft forward. A turbofan is very similar to a turbojet, but it has instead of a small compressor, it uses a very large fan in front of it to generate the thrust. A prop fan is a turbofan, except the fan is on the back of the turbojet instead of the front. And these are all used in air breathing applications at subsonic speeds, or speeds less than the speed of sound. Now, if you want to go faster than the speed of sound, or supersonic, you have to use something called a ramjet or a scramjet. But these are very complex, and you'll save them for a future episode when we talk about compressible flow. Now, all of these methods of generating thrust rely on air, and they're called air breathing. You only carry a fuel and not an oxidizer to provide oxygen for the combustion. But what if you want to go to a place that doesn't have air or doesn't have oxygen in order to combust? Well, then you'd use a rocket. There are two different types of rockets, or three, that is. There is the hybrid, the solid, and the liquid-fueled rockets. And how a rocket works is that it takes an oxidizer, which provides the oxygen for the combustion, and combusts it with the fuel. And that's why they're used in space travel, because if you're going to outer space where there's no oxygen or no air, how are you going to generate thrust? You need an oxidizer, and that's what they use. But we'll talk about rockets in a future episode and the different types of rockets.
So, in this part of the podcast, we're going to be taking listener questions that you guys may have with regards to the topic that we discussed. At the moment, we don't have anything right now, but if you guys have any questions, make sure to ask them in the comments and we'll make sure to address them in future episodes. If you guys want to learn more about this topic, make sure to check out The Fundamentals of Aerodynamics by John Anderson. It doesn't really matter which edition you use. The subject is really, really good in that.
And if you want a free online source, please check out NASA's Beginner Guide to Aeronautics. You have that linked in the description below.
And last but not least, if you guys are really looking towards experimenting with lift and drag and all these different parameters that we talked about, check out XFLR5. It's an open source program created by MIT that's used to analyze airfoils. Well, folks, I hope you enjoyed today's episode. Be sure to ask us any questions you may have thought of in the comments below, and we'll make sure to address those in the next episode. On behalf of my co-host, Ryan, we'd like to thank you for listening today, and we hope to see everyone again in next week's episode. Thank you, and goodbye.